So the DTFT, it's a continuous frequency and it's infinite in length. And it exists if, just cut this section off to make it clear we're talking about something new. And it exists if and only if x of n has finite energy. And remember, energy is the energy of a signal x is defined to be the summation over all n of the magnitude of x of n squared. And that has, so what we're saying is that energy has to be less than infinity for the DTFT to exist. So as an example, 1/2 to the n u of n, that's okay. 2 to the n u of n, not okay. That summation would be infinite. It's periodic in 2 pi. It's conjugate symmetric around pi. Conjugate symmetry means that the magnitude will be the same and the phase will be odd. So you'd have to invert, excuse me, you'd have to invert the phase angle around pi. Same thing for real versus imaginary, even though we don't talk about that rectangular breakout much. The real part would be symmetric and the imaginary part would be odd around pi. So point of confusion, it's easy to get confused that omega equals, when it's 0, that's DC values, and it can go all the way up to pi, which is your highest frequency possible, and it goes back up to 2 pi, which is back to your DC, and you measure it. That's not the confusing part. Excuse me. That's not the confusing part. The confusing part is that it's measured in units of radians per sample. So if you have a 2 pi radians per sample, then you've entirely gone around the circle and you've got it back to a DC level. Now if you were to graph the DTFT, this is on the horizontal axis. If you were to graph the angle of the DTFT, and this is something we haven't done as much, but if you were to graph the phase angle of it, that thing is measured in rads. That thing is measured in radians, not radians per sample. And this is a vertical measurement. Up here at the top, you might want to measure this. And so while omega is measured in radians per second, which is a horizontal measurement, this is measured in radians. We talked about the energy density spectrum. And the energy density spectrum is S x x of e to the j omega. It's a function. It's a continuous function in omega, and you can calculate it as just the square of the magnitude of the DTFT. And what it's saying is that the units of this energy density is what if x of n, excuse me, if x of n is a voltage that's across a 1 ohm resistor, then the units of the energy density spectrum is watts per radians per sample. So it's a measure of the amount of energy that's in a frequency band. So if you integrate this between 2 frequencies, then that's the amount of energy in your signal between those 2 frequencies. And or it's proportional to the energy in your signal between those two frequencies. And so it should kind of make sense that if you integrate SXX, that energy, over all unique omega, it should equal the total amount of energy in your signal that you found up here in the time domain, where this is a frequency domain amount of energy per unit radians per frequency unit, and this is a total amount of energy in your signal. And I just need to tell you the area to integrate it over. And there's also there is a corrective factor out here. And that's Parseval's theorem in the discrete domain. And then we talked about tables, properties, and symmetries. Remember, the big thing about symmetries here is that if you've got a conjugate symmetric x of n, that gives you a real DTFT. And similarly, a conjugate antisymmetric x of n gives you an imaginary DTFT. And then how do you graph using MATLAB? You use, that's the freak Z command. And that assumes that you already know what the DTFT is, and you put in the numerator coefficients, the denominator coefficients. So as a particular example for this one, the numerator coefficients would be 2, 6, and 3. The denominator coefficient would be 1. And then you put in your range of omega for which you want it calculated, and it will pop out the DTFT, which is just this thing evaluated at those different omegas. And then you can graph those. And you know that when you graph those, you'd want to, if you call all this equal to, say, capital X, then you'd want to plot your omega versus some part of your X, maybe the magnitude of your X. You wouldn't want to stem it because, again, X is a continuous frequency. All right, that was a lot of stuff on the DTFT. Let's do the same thing for the DFT. Any questions on the DTFT?
Sir, just a quick question. It's
Shoot.
kind of an aside.
Yeah.
For the lab time, after you've answered questions for the lab and no one else has any more, are we able to work some problems out during that allotted time period?
Yeah, I'll be happy to work anything you want. It's your time.
All right. Thank you, sir.
Mm-hmm.